Hey, it's Dr. J. I'm back with part 2 of the Pythagorean Theorem. Ran out of time yesterday, so finishing it up today with a lot of applications and a slightly different approach with some of the questions. I know the last example I did in part 1 got a little sketchy at the end, and since it is in the homework, I'm going to give you one more example. I'm going to start example 1 with a similar problem to example 12 in yesterday's video. So this is just a classic word problem. Let's change the numbers a little bit. The shortest side, a right triangle, is 8 centimeters this time. Although it really doesn't make too much difference what units we're using, but I like to vary the units. In chapter 6, we'll get more into the details of the different types of rates and units and measurements and things like that. So in this lesson, just everything should be centimeters. So the shortest side of a right triangle is 8 centimeters. Very similar setup. The difference between the other two sides is 2 centimeters. Find the lengths of the missing sides. Or the unknown sides, or whatever you want to call it. Okay, so we read it, maybe draw a picture, translate it, solve it, and we learned last time that checking is very important as well. I don't know if you can see that. Blocking it. Read, translate, read, draw, translate, solve, and check. Okay, RDTSC. Sometimes we skip the drawing if you have a good understanding of what it looks like. In this chapter, I'm doing a lot of diagrams, so start off with a triangle. Right triangle. Just get an idea of what everybody is. The shortest side is 8, so that's going to be 8. The difference between the other two sides is 2. All right, so that would be C and B. Those are the other two sides. Since C is the hypotenuse, it's the longest side, you have to put it in this order. C minus B is 2. All right, so very similar to the last time. You want to solve this one for C. You could actually just do this mentally, all right? If the difference is 2, well, then that means the hypotenuse is 2 more than the base, yeah, because their difference is 2. So you could just jump right to this if that makes it a little easier for you. I like to show the logic behind that. All right. And then I want to do something slightly different this time. Since we haven't really spent a lot of time with more than one variable, and this technically has more than one variable, the very first thing I'm going to do before I even use the Pythagorean theorem is I'm going to come over here to my hypotenuse, and I'm going to remove the letter C completely and just replace it with B plus 2. All right? Because C is, you can read the equal sign as is, C is actually B plus 2. So why don't we just get rid of C altogether and just do it now? Yeah. Okay. Now we'll use the Pythagorean theorem. That's the workhorse of most of these problems. So we have C squared equals B squared plus A squared. Remember, A is 8. And notice for C, I'm not going to actually write the letter C. I'm going to write B plus 2 in the position that formerly was known as C. All right. If you get to solving an equation anywhere in this course and there's more than one variable, you can't solve it with more than one variable. You need to remove or eliminate, or in this case we call substituting. Substitute, or replacing the variable c with b plus 2. Okay. Now you got to remember here, when you square a binomial, it has two terms, you want to write it out twice. You're basically multiplying b plus 2 times itself. And I guess we can go ahead and do 8 squared while we're at it and make that 64. All righty. Now we're going to distribute, or also known as foiling. So we're going to go b times b. It's going to be b squared. We're going to do b times 2. That's going to be 2b. We're going to do another b times 2, which is another 2b. I guess you could say b2, but that looks funny, so we call it 2b. And then finally, 2 times 2 is 4. All right, so this is the equation that we're actually going to solve. I'm running out of space, so I'm just going to erase a little bit of this stuff here. In fact, I'm just going to erase the whole question and give myself some room to work. And this is where I screwed up last time. When I got to here, I had written one of the numbers incorrectly. But since I'm refreshed today, I think I'll be okay. So I'm going to just copy the entire equation. B squared plus 2b plus another 2b plus 4 is equal to b squared plus 64. In the next level of algebra, you'll solve more complicated versions of this. They'll have, maybe negative signs. The exponents might get a little more complicated. In this section, since we haven't really gotten into how to solve what are called quadratic equations, all of these examples of this form, when you move the b squared over, you're going to subtract b squared from both sides. These will always cancel out. So if you still have a b squared in this type of problem, then you've made some sort of error, and it's an indicator to fix that. So you get 2b plus 4 equals 64. Last time I combined these a little sooner. In this version of it, I'm deciding to wait till the end. I'm going to combine 2b plus another 2b. That becomes 4b. All right. And at this point, it's just a basic one variable. We call this a linear equation. It has no exponents. It shouldn't have any fractions. I've pre-programmed these problems so that there should be no fractions. You're going to subtract 4 from both sides. Not that you couldn't handle fractions. I'm sure you could. We've done a lot of problems with fractions, but in this section, at least at this stage, I'm avoiding them at all costs. So I'm subtracting 4 from both sides. So now I just have 4b is equal to 60. And you know what to do here. You're going to divide both sides by 4 to get the b by itself. So you're going to get b equals 60 divided by 4 is 15. Okay. And that's really it. It's really about solving one variable. It's usually b for this particular example. Not always. Sometimes we solve for c. There were some other problems where we solved for a, but in this particular one, we're solving for b. So we know now that b is 15. That's our b. All right. And then you just do a little mental math. If B is 15, then 15 plus 2 is 17. So C is 17 because C is 2 more than what B was. All right. So I read it, I drew a picture, I translated it. This is the translating into algebra part. Then I solved it. So most of the translation was here. That was the translation. And then I started solving it. I finished my solving up here. Once I have B, you've heard me say this before, buy one, get one free. So if you solve for B correctly, you should, for free, get C, as long as you understand what you're actually doing, reading the question carefully. Okay, so let's go ahead and check our equation. Let's go ahead and check up here. So we have C is 17, B is 15, and A was given to us as 8. All right, this is the hypotenuse. This is the longer leg. And A is the shorter leg. All right. Now in your homework, you could just type it in and see if it marks it correct. But if this was a test question, I would recommend checking it using the hypotenuse squared is equal to the sum of the squares of the other two legs. Remember, that's Pythagoras' theorem. If and only if. If this is true, then that means you've done it correctly. So this is a verifiable process. So let's just see. 17 squared is equal to 15 squared plus 8 squared. Notice yesterday I found my mistake by this process. I honestly would have never noticed. You know, by the time we got that far into it, I was ready to just press stop, which I'm glad I didn't do. Calculator probably comes in handy. 17 squared is 289. That's not one I typically memorize, although I bet you have these memorized. 15 squared is 225, and we already know 8 squared is 64. Real quick check. 225 plus 64 is in fact 289. If these sides do not equal each other, these values do not equal each other, then you must have made a mistake. But we didn't. It's good. So it checks out. Very good. All right, I don't know about you, but I feel better now. I had a rough go of it yesterday. But today, starting off fresh. All right. That's about it for that particular type. The rest of these examples that we're going to do are all going to use some geometry that we should know from a previous sections, just basic geometry. Let's start off with a circle, or in particular a half circle. So example 2. A shaded half circle. It's actually called a disk. You really want to be the life of your next party. This is a circle, yeah. But when you shade it in, we call that a disk. It's a shaded circle. It includes the interior of the circle. Now we're only going to do half of one. So half of a disk, shaded. Maybe I'll shade it in blue or something. Does blue show up on the camera very well? So a shaded half disk has an area. Sorry, a shaded half disk is on the hypotenuse. We're going to try to find the area, the hypotenuse of a right triangle. So this is on the hypotenuse of a right triangle. All right. The length of the A side is 7 0.0 meters. And the length of the base is 9.2 meters. Find the area, we covered this in a previous section, of the shaded half disk. Let's round to the nearest tenth. All right. So a quick refresher, the area of a circle or a disk, so the inside area, is pi r squared. So a half disk would be pi r squared over 2. Area half disk equals pi r squared divided by 2. So this example uses decimals and fractions, but since I'm rounding at the very end, I'll convert all this into a decimal at the end. So notice what we don't know. We don't know r. We don't know r. So r is the radius from the center of the hypotenuse all the way to the outer edge of the disk. Now I drew my radius going up. You could draw yours going down. It's up to you. Okay. So notice r is half of the hypotenuse, the length of the hypotenuse. I'm just going to say hype for short for hypotenuse. So notice that r is half the length of the hypotenuse. All right. So we're going to find the hypotenuse, then divide by 2. All right, that's kind of our strategy here. This is our plan. Our plan. Got to make a plan. And I'm going to need some space to work here. Let's save this formula for later. Remind me not to erase that. We're going to need that formula at the end. All right, so let's find c. We got c squared is b squared plus a squared. B is 9.2. Again, don't worry about the units. The units are meters in this case. It's a very large shape. 9.2 squared plus 7.0 squared. You know, if it's 0.0, you could just leave it as 7. But since I'm using decimals, I might as well just use decimals for everybody. So we got 9.2 squared. That's going to be 84.64, or 84 and 64 hundredths. And we got 7 squared, which is 49. And again, technically it's 0.00 if I were to do it all out on the calculator. Or you could just write 49. So we'll add those together. 49 plus 84.64. C squared is 133.64. So C is the square root of 133.64. So C is approximately 11.56027, blah, 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 blah. Now, one hint or piece of advice that I would give you when you are rounding, don't round now. All right? I know the instructions say to round to the nearest tenth. One of the reasons why I wait until the end to read it or write it or even do the calculation is if you do it now, it'll be incorrect. So don't round yet. It'll make your answer off a little bit. All right. So we found C. Good. So that means R must be half of C. So 11.56027 divided by 2. Yeah. So divide that by 2. And that's going to give us our radius. It's half of the hypotenuse. That's 5.7801, blah, 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 blah. You should probably keep at least 4 places, and then we'll go to the rounding to the nearest tenth when we're done. All right, well, the hardest part is done. Hardest part is translating it, understanding the geometry here, solving using the Pythagorean Theorem, which is the whole lesson. And then at that point, it's just using the recipe. So you're going to put your radius inside of this half disk formula. Let me just rewrite it. Area. I'm just going to write the word area. We know it means the half disk. It's going to be pi times 5.7801 squared divided by 2. You could use old school division, like, on an elementary calculator, or you could use fractions. But you do need to follow the order of operations. So first you're going to square that. 5.7801. I wish I had a fancier calculator today. I probably have one somewhere. So the area is pi times 33.4095. And then divided by 2. And I need this space here. Now the order of operations, I should probably do everything in the numerator and then divide it by 2. Although it turns out in this particular example, you could divide by 2 now, but I'm just going to wait till the very end. Sometimes you get a pi button on your calculator. I know some of the smartphone calculators have that. I don't have one on here. So I'm going to go 33.4095 times 3.1415. I'm using a little bit larger or more decimal place version of pi. 3.14159 would be very common. So I'm going to multiply that by 33.4095 times 3.1415. You could probably get away with just 3.14. So I'll put that in my notes here, but when you're calculating decimals, it's always better to have too many decimals and then round them later than it is to be cheap at the beginning and not use enough. So you're going to multiply that. I got 104.9559 divided by 2. And so I get approximately 52.47. 7, blah, 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 blah. But now I'm going to do my rounding. So rounding to the nearest tenth, we're going to look at the 100th place. That number is larger than 5, so we're going to cross it out and change the 4 into a 5. So we've got 52.5 square meters, or m squared. Think of it as, carpet or tile or some kind of, flat surface. It could be grass. It could be, dirt. It's how many square meters would fit inside of this half disc. I'm not going to fill it all up with squares. Although anybody that's ever tried to lay square tiles in a round room, might be some reason why we don't make rooms round very often, because it's very difficult to do that. But you would need 52.5 of these squares if you were trying to fill out the whole thing, and you probably would use a cutter and try to cut some of them into odd shapes in order to fit it all in there. Most of them would be square, but you would need some funny shaped ones here in the corner. All right, so that's your area. It's the area of the shaded half disc. Grab a new pen. That's this one. That's a good one. All right. I must be on a theme here with these, construction type projects. I don't know if you think of this as, building something out of actual material, that this would be what you would need to purchase or supply yourself with in order to do it. The next one, I'm going to be doing a roofing problem. So, how long is the edge of a roof? Do you say roof or roof? I say roof. Some people say roof. Find the length of line segment AB. So I'm starting to use what's called the classical notation. This is classical geometry. In classical geometry, we don't name the sides with letters. We name the vertices with letters. It's the way Pythagoras would have done it, 2,500 years ago. So I want to know the length of line segment AB. Now, you might not see a triangle yet, but you will. Let me draw the rest of the building. So this is sort of a profile of a shed or something. So this is 10. Let's go to feet, 10 feet. We'll call this edge, or this vertex, C. This edge is 9 feet. This edge is 1 foot. Sort of the overhang of the building. And this edge is 4 feet. So you got a 1 foot overhang. Now you can kind of see the profile of like a shed or maybe half of a house. And I want to know the length of line segment AB. So how long is the edge of the roof or the roof? Now, we've done problems like this before, but they didn't have triangular edges, right? If you remember some of the previous geometry problems that we did, they were all what are called rectangular, rectilinear. They all had square corners. They were built out of little boxes. But now we have a combination of boxes and triangles here. We're basically going to use the same method. It's called dissection or dissection. In science, they call it dissection. In math, we call it dissection. It just shows a slight difference in our emphasis. Okay, let's draw a triangle. So we have a triangle here. This is what we're looking for. Yeah. This is our right triangle. I like to cut it off and remove it from the picture. It sort of abstracts it. Don't worry about the scale or the size, as long as you've got the right general shape. All right. So we know that this side, the A side, is the difference between 10 and 4. Because this is 10, and this is 4. And so to find the remaining side, we subtract 10 minus 4. And we know the B side. Now this is where it gets weird with the lowercase and the capitals. Typically capital letters represent corners or vertices. Lowercase letters represent edges or sides. Okay. The one that gets weird is the letter C. You probably remember that. When you're writing very quickly, a capital C, lowercase c look the same. So you got to be a little bit careful. So B, let me use a different color here. B is this side here. Yeah. B will be 9 plus 1. Yeah, because I got 9 feet here plus another foot here. So 9 plus 1 is my B. Might as well stay true to the color here. So there, 9 plus 1. When you are solving these problems, your dissection is the most important part. You got to make sure you keep everybody in their right position. You calculate who everybody is. So B is 10 and A is 6. Okay. So what are we looking for? We're looking for the hypotenuse C. If this drives you crazy, using the letter C 2 different ways, you can choose a different letter. We can call it H. Yeah. If it doesn't bother you, then keep it as C. I might as well use H for hypotenuse. Yeah. I always wonder why we just don't use H in the first place, right? You could. So you got H squared, which is the same thing as C squared. Equals B squared, 10 squared, plus 6 squared. There's your Pythagorean theorem in relation to this diagram here. These are easy values to calculate in your head. You get 100 plus 36. H is the square root of 136. I can't do the square root of 136 in my head. It's 11.6619. I'm going to stay true to the last problem. We're going to round to the nearest tenth. That's the most common rounding that you've seen me do, but sometimes I'll change it up just to make sure you're reading it carefully. So we're going to round up, throw away the 6. We're going to round the 6 to a 7. And so we're going to get the hypotenuse is approximately, but now I'm going to call it AB. Yeah, AB is approximately 11.7 feet. AB is H, right? It's the line segment AB. So there we go. The length of that roof is 11.7 feet. Approximately 11.7 feet. I still haven't figured out how to put the approximately sign in your homework, so it'll say equal, but when you're rounding, your equalities are approximations at that point. Well, for the rest of the problems, we are going to put away the calculator, and we're going to go back in time, and we're going to do what's called classical geometry. A classical geometry would be the classic way to do geometry as you would have done it, 2,000 years ago without a calculator. But we will continue to use this notation where we identify the vertices with capital letters. And that will be our finale, what's called classical geometry. No electric guitars, no special effects, just classical geometric shapes. Some people will call it the old-fashioned or the old-school way to do it. All right, example 4. So in classical geometry, no calculators. And that's not only a suggestion, that's in fact a rule in classical geometry. If you use your calculator and type it in using a calculator, I'll know immediately, the computer will know, and it'll mark it wrong. And you'll be getting frustrated going, why am I getting this wrong? I know I'm doing it right. So that's not just a suggestion. That's the law of classical geometry. Some folks start with classical geometry when this is taught. Example 2, find the exact length of AB. So A, B, C. In classical geometry, C is always the right angle. A and B are the vertices or the corners, and they can be interchanged. Right? So AB, or I could go BA, means the same thing. But C must always be the right angle in classical geometry. Easy way to remember that, it's the opposite of the hypotenuse. So this would be lowercase c. Okay. This would be lowercase a, opposite of capital A. And then this would be lowercase b, opposite of capital B. All right, so we're trying to find lowercase c. Yeah, so the line segment AB is lowercase c. So we got c squared equals b squared plus a squared. Probably have that memorized by now. You might also memorize it as a squared plus b squared equals c squared. That's just reading it this way. A squared plus b squared equals c squared. I read it the other way. C squared equals b squared plus a squared. Tomato, tomato. Now, no calculators here, so do it all by hand. You got 9 squared plus 2 squared, 81 plus 4, 85. Take the square root, but don't use your calculator. This is what we call the exact length, the square root of 85. If you put it into your calculator, you're going to get a decimal, and it's no longer exact. So we call that the exact length of the hypotenuse. The square root of 85. Now, in your homework, I don't use the letter C, so this is actually AB. Yeah, capital A to capital B, the length of that line segment. The little lowercase letters are just there to refresh your memory from the very first example I did in part 1, so that you know what formula you're actually using. I mean, I guess there's a classical version. I'm going to regret writing this down as soon as I do, but I'll do it anyway. The classical version of the Pythagorean theorem would be AB squared equals AC squared plus BC squared. But nobody uses this. I shouldn't say nobody, but I mean, I don't use this version, because why would I want to write 2 capital letters each time when I could just write 1 lowercase letter, right? And so we want to be somewhat efficient, but you also want to be correct as well. So this is the classical Pythagorean theorem. Okay. A couple more of these, and we should be able to wrap this up. So much here, I'm afraid to erase it too quickly. So take a good look at it, and let's continue with the classics. Example 5, find the exact length of BC. I guess there's one thing that I didn't mention last time. The entire triangle is called ABC. That's the name of the triangle in classical notation. So again, A is typically down here, B is up here, and C is always the right angle. So this time we want to know the length of BC, this edge here. I'll give you the hypotenuse is 7, and the base side is 5. So I like to switch from capitals to lower cases. So the hypotenuse is lowercase c. The base, AC, is lowercase b. By the way, another way to remember it, the lowercase letter is whatever letter the other two letters are not. So if this is AB, well, then that's C. If this is AC, well, then that's B. Yeah. And if this is BC, well, then that's A. It's the un letter, the letter that's not there. So that's what we're looking for is A, lowercase a. It's been a while since we did this, so let me show you this one more time. If I'm looking for A, then I put it in alphabetical order. A squared plus B squared equals C squared, because I'm looking for A. And then I move the B squared to the other side. And you may have already memorized this version, A squared equals C squared minus B squared, or not. As long as you know the original version, you can use that as a generator of all the other versions of the formula. So I've got A squared is my unknown. That's what I'm looking for. I'm actually looking for A, but start off by doing A squared. If you've already forgot my advice from yesterday, don't take the square root yet. If you do it now, it'll usually screw it all up. So we got C squared is 7 squared. We got B squared is 5 squared. Again, no calculator is necessary here. 49 minus 25. That would be 24. Now that's not A, that's A squared. I'm going to take the square root, cancel out the square, and don't actually do it. The exact length is 24. And of course, that represents BC is the square root of 24. All right, so again, the letter A is only temporary. It represents this side BC. Now, this is what we call unsimplified exact. Unsimplified exact answer. For the last couple examples, I'm going to give you the simplified exact answer. So we got to look for whether or not I'm saying exact or simplified exact. So let me just give you a really quick, I won't call this an example yet. If you are asked for a simplified exact value, and the key word there is just simplified. You see that in there. If you don't see it, you'll assume unsimplified is okay. So in other words, in math, it's not just me, but in math, if I don't say simplified, well, then that means you can leave it unsimplified. It's unwritten. You didn't say simplified, so it's unsimplified is okay. But if I say simplified, you have to simplify it. I don't think I asked for the simplified one on simplified exact on this problem, but I'm going to show you it anyway, just so that you know it. This is actually the end of that particular example. So if you're asked to simplify it, then you take your square root, square root of 24, and you break it up into two smaller square roots. All right. One of them must be perfect. Remember, perfect squares are what we covered in the introduction to square roots. 4, 9, 16, 25, 36, 49, all the ones you memorized when you were little. Or when it was time to memorize them. So what number goes into 24 that's perfect? The other one doesn't have to be perfect. Not a perfect square. This one must be a perfect square. As I've been talking, you've probably been thinking about it. 24 is 2 times 12, but neither one of those are perfect. 24 is also 8 times 3, but neither one of those is perfect either. So the one you're going to pick, there's always only one good one. The one you're going to pick is 4 times 6. If you want, you can put a little dot there for times. So there's lots of wrong simplifications or incorrect ones. You want to pick the one that has one perfect and one imperfect. All right, so the perfect square becomes 2. No calculator, all right? Even 2,000 years ago, without calculators, we knew, or it was known, that the square root of 4 was 2 without a calculator. Now 6, on the other hand, Pythagoras himself wouldn't have known how to simplify the square root of 6, believe it or not. No, had no idea how to do that. They would just leave it as the square root of 6. Very difficult to calculate square roots in ancient times. That's why they typically avoided non-perfect numbers whenever possible. So that would be it. We typically don't put the multiplication symbol. This would be simplified and exact. 2 root 6, that's the way we say it. 2 root 6. Typically, when we're doing square roots, we just say root. It's a quick way to say the square root. There are other roots that you'll learn about next semester, but in this semester, the only root you need to know is the square root. Well, that's classical geometry. I remember many years ago when I first started in this profession, the most common thing I would hear from students, in the 90s and when I first began was, I was really good at math until we got to geometry, and then I completely lost it. That was very common. I don't hear that so much lately. What I mostly hear these days in the feedback that I get whenever you provide feedback is I hate word problems. That's become the new geometry of the day. But maybe you hate both. Maybe you like them both. I don't know. Whether you like it or not, we're doing it. All right, so example 5. It's going to be a much shorter list of examples this time. Find the length of AC. Okay, so this side is the square root of 20. Got blurry all of a sudden. That's AB. All right. And this side is 2. Oh, no, 3, sorry. I was looking at the wrong number. 3. This always happens at the worst possible time, doesn't it? Find the length of AC and come back to me. There we go. So find the length of AC. Now, if possible, what I'll put over here is I'll say simplify if possible. Although I really could just say simplify. Of course, I can't ask you to do something that's impossible. So sometimes I'll say simplify if possible, or simplify if necessary, or just simplify. All right, this one's a little tricky because I put a square root in the original problem here. So that makes it a little bit trickier. All right, but that's okay. We got it. Let's label everything. Remember, across from capital C is little c. Doesn't look very little, does it? Let's do little c. There we go. Across from capital A is little a, or lowercase a. And what we're looking for is lowercase b. That will be AC. All right. Now again, there's the Pythagorean Theorem, but there's all these different formulations of it. We're looking for b, so I'm going to go with b squared plus a squared equals c squared. It means the same thing. It reads nicer because we're trying to find b. And then you want to get b by itself, so we're going to put a over there. All right. B squared is, now we got to be careful here. We're putting the square root in of something that's already being squared. So you got to be very careful there. So I'm using parentheses just to be extra safe. Oh, sorry. It's not, it's 20. Yeah. I'm already wearing myself out here. So it's the square root of 20 goes inside of the parentheses. Now we did this in 5.7, right? Before we even learned the Pythagorean theorem, we were just generally learning how to do this. If you square something that's already a square root, it's called extracting. So you do not actually square the radicand. You just extract it, and that's what you have as 20. Now this one you're actually squaring because it's 3 squared, which is 9. B squared is 11. Square root both sides. So b is the square root of 11. The square root of 11 cannot be simplified, so it's already simple and exact. Yeah. How do you know whether something can be simplified or not? Well, you look at it and you ask yourself, is it divisible by 4? Nope. 11's not divisible by 4. Is it divisible by 9? Nope. And then the next number is 16, which is larger than 11, so you don't even have to try 16, because how can something be divisible by something that it's smaller than? So you just mentally run through all the numbers that are perfect, which there aren't very many, right? 4, 9, 16, 25, 36. I mean, it just takes a couple seconds to run through them. Once you've passed the number that you're dealing with, once you get past 11, if none of the previous numbers go into it, then that means it's already simple. All right. So numbers that can be simplified are things like 18, right? If this was an 18, I could have done it because 18 is divisible by 9, and 9 is perfect. Right? What's another one? 50. Yeah, 50. If this was a 50, 50 is divisible by 25, so that could be simplified. But 11 cannot be simplified. It's already simple, so it's done. Okay, the last couple examples, we're done with this particular presentation. We're going to start talking about the angles. All right, so this is an introduction to trigonometry. Just a brief introduction. We do teach an entire course. It's called Math 5. If you're going on mathematics, if you're planning on taking calculus or pre-calculus, you're going to need trigonometry. I'm not teaching a course on trigonometry right now, but I'm giving you a brief introduction to it. Okay. We're also going to talk about triangles that might have two sides that are equal. It's called an isosceles triangle. And we're going to also talk about a triangle that has all three sides equal, called an equilateral triangle. We'll handle those one at a time. All right, so first thing I want to give you is a little fact about all triangles, not just right triangles. Well, you can really, the smoke is blocking the sun. There's a fire today in Indio. I don't know if you just noticed that. Just all of a sudden the smoke came over and got it really dark. My board turned dark on me. Unless you're watching this video in a week or two, and then that comment will mean nothing. Okay, a fact about all triangles. Doesn't matter whether it's a right triangle or not. All triangles have this fact. This goes back to the very beginning of 5.8 when I taught you about the different terminologies about triangles. All triangles, if you add up the angles, all right, and again, this is not a right triangle. This could be any triangle. We typically name the corners, also known as the vertices, the same letter as the angle. So this is vertex B. This is also called angle B. Yeah. Sometimes we put a little angle sign here to say angle. It looks kind of like an alligator less than sign. So angle A, angle B, angle C. All right. So those are inside here. Angle A, angle B, angle C. Here's the fact. The sum of all these angles always sum to 180 degrees. So if you add them up, angle A plus angle B plus angle C, you always get 180 degrees. There's a long description and explanation of why that's true. I will spare you that at this point. I just want you to know it's a fact, also known as a theorem again. Interior angles theorem is the fancy way to say it. So when you add up all three interior angles, you always get 180 degrees. Okay. So we're now going to talk about what's called an isosceles triangle. If two angles are equal, we call that isosceles. If two of the angles are equal. Doesn't matter which two. Any of these two angles could be the same. We call that an isosceles triangle. So let's do example 6. Given the isosceles triangle, ABC. Some people use a triangle symbol here like this. I just say the word triangle. With angle A equal to 45 degrees and angle C equal to 90 degrees and side AC equal to 15, find the missing angle, which would be, I guess, angle B is missing, and the missing sides. If we have AC, that means we don't have AB and we don't have BC. Those would be the missing sides. Okay, so what should we do here? Let's draw the triangle. Read it, draw it. I'm going to save this space down here for calculating. So we have an isosceles triangle. It means that two of the sides are equal. Angle C is 90 degrees. So there's my 90 degree right here, angle C. Angle A is 45 degrees. Okay. Angle B is the unknown angle. But remember, we have our fun fact. Angle A plus angle B plus angle C is 180. If you're quick with mental math, you already know what it is, but I'm going to write it out in all its detail. We know angle A is 45. We don't know angle B. We know angle C is 90. Yeah. So if you add up the 90 and the 45, you're going to get 135. And now you're trying to figure out the missing angle B. Subtract 135. And there you go. If you're a visual person, you saw the triangle, you immediately knew this one was 45 as well. Because I said it was isosceles, that was a big hint. If it's isosceles and this one's 45 and this one's 90, well then the other one had to be 45 because there are two angles that are the same. Okay. So that takes care of that. Now we know that the side AC is 15. Now I have to apologize for my drawing. It's not to scale. If the angles are equal, these two angles are equal, then these two sides must be equal. Right. Not these two, because look, clearly the hypotenuse is longer than 15. And again, if my picture were to scale, it's actually to scale from my perspective, but my camera is at an angle, so you can't see that. All right. So I automatically know that BC is equal to 15. That's basically a free answer. Another way to remember isosceles is it has two equal angles and two equal sides. But you really only need to remember that it's got two equal angles. If these two angles, now it's kind of easy if you think about it. Well, easy is a rough word. It's intuitive, maybe. I don't know. If this is capital B, well, then down here is lowercase b. And if this is capital A, then over here is lowercase a. And so if angle B is equal to angle A, well, that means side lowercase b is equal to side capital. Sorry, side lowercase a would be equal to side lowercase b. So what's the only thing we don't know? The only thing we don't know is the hypotenuse. Yeah, the hypotenuse is AB. Yeah, also known as lowercase c. Or if you prefer, you can use H for hypotenuse. The reason why, there really isn't a good reason. We use H for other things in mathematics, so we typically don't use it for hypotenuse. But I mean, I did. There's no law that says you can't. I just didn't. Okay. Let me document everything that I know. I know angle B is 45, so that's done. I know BC is 15, so that's done. That was my free answer. In fact, 45 was kind of free also because I told you it was isosceles. So the only thing we're trying to find now is the missing side AB. Or in other words, lowercase c. So I've got c squared. Again, these are lower cases now, is a squared plus b squared. A and b are the same. So it's 15 squared plus 15 squared. Classical, no calculator. 225 plus 225, which is 450. All right. Then I take the square root. So that cancels. I get c is the square root of 450. And simplify if possible. So let's see, 450. Is it divisible by 4? I don't think so. Yeah? Oh, you can't see that. I'm trying to be classical about it. 450 divided by 4. 1, 4, 0, 5, 4. Nope. 4 goes into 10 2 times. 2 times 4 is 8. You know what? If you did use your calculator, I wouldn't know. So it's not divisible by 4. I think it's divisible by 9. I should have just done that to begin with. 450 divided by 9. 9 goes into 45 5 times. 5 times 9 is 45 exactly. Remainder 0, so put this up here. 9 times 50. So I've got the square root of 450 is equal to the square root of 9 times the square root of 50. So it would be 3 square root of 50. Keep going. Keep going until you must stop, or until you can't go any further. Further or farther? I don't know. Further? Farther. More. Okay. 50 can be simplified. 25 times 2. Yeah, the square root of 50 is 25 times 2. So the square root of 25 is 5. The square root of 2 cannot be simplified anymore. Three times 5 is 15, so I have 15 times the square root of 2. You know, I probably would give it to you if you just put the square root of 450. I don't know. I'd have to make that decision based on how clear I thought the instructions were. But I'm really trying to end this with the process of simplifying square roots in the classical sense. So this is AB. I'm going to summarize everything. BC was 15, and angle B was 45 degrees. There is no degree symbol in the box, so the degree symbol will actually be outside of the box. Haven't figured out a clever way to have you guys type the degree symbol, so I'll just have it there for you already. Okay. Well, that's an isosceles triangle. All right. You might notice a pattern. This happens with these types of 45, 45. That particular angle, 45, always yields one of the sides is the square root of 2 times the other side. So if you choose, you can just memorize. This is optional. In the course trigonometry, it's no longer optional, but it is optional in this course. You could just use the Pythagorean Theorem, which is all I'm really holding you to. If these are 45, and again, my drawing is not to scale, and these sides are both x, they should be the same, then the hypotenuse is x times the square root of 2. So you kind of get a free answer there with a 45-degree triangle. We call this a 45, 45, 90 triangle. Also known as one example of an isosceles. There are many isosceles triangles, but this is the isosceles, the one that I'm demonstrating. I'm not going to do any more isosceles examples. All right. I guess I should wrap this up. I want to show you the equilateral triangle. So that's done. There's your answers here. The equilateral triangle, example 7. All right. So, in an equilateral, before I do the example, let me give you the definition. I should probably just start there before I get too far ahead of myself. An equilateral triangle all the angles are equal, all the sides are equal. Okay. So we call that equilateral. All angles are equal, all sides are equal. And again, my drawing is not to scale. Slightly askewed because of the camera angle, but I can try to try a little harder there. I try. Remember, the drawing is just a reference anyway. Okay. So remember, angle A plus angle B plus angle C is equal to 180. Okay. Angle A is equal to angle B is equal to angle C. So these are all three equal to each other. So what we do is we just call them all A. A for angle. If they're all the same, I'm just going to call them all A. I could call them all B, and I could call them all C, but we typically just use A for equilateral triangle. All the angles are equal. So you have three of these angle A's. If the symbol for angle drives you crazy, you don't have to use it. You could just say 3A. All right. It kind of drives me nuts because it looks like an inequality, an alligator, crocodile, whatever we used to call it. If it doesn't bother you, a classical way to do it would just be to use parentheses like that, and then you can keep the angle symbol there. Needless to say, we're going to divide both sides by 3. You probably could have done this mentally. All of the angles are 60 degrees. Okay. Now, all of the sides are equal, but they're not all going to be a particular number. A could be any real number. Technically, it's a positive real number. We don't draw triangles with negative numbers. So angle A, all three of these angles, or you can call them A, B, and C, they're all equal to 60 degrees. The sides, lowercase a, are all equal. And they could be any positive number. So now I can actually do the final example, example 7. And I will give you one of the sides, but I will essentially be giving you all three of the sides. Okay. Example 7. Suppose triangle ABC has angle C equal to 90 degrees, also known as a right angle. Yeah. And angle A is 30 degrees. side BC is 8. Okay. Now 30 degrees, I'm intentionally using 30 degrees here. I'll typically either give you a 30 or a 60 somewhere, because it has to be a multiple of 30. It's either 30, 60, or 90, right? Now 60 would be equilateral, so let's go ahead and draw it like this. It's probably going to drive you guys crazy, but I'm going to stand my triangle up like this. This is C. All right. Now I'm going to put A down here. Oh, no, actually I'm going to put B down here. Sorry, and A up here, because A is 30 degrees. 30 degrees. All right. And then side BC is 8. And this one's 90. So where is the equilateral triangle? Can you see it? Right, remember, an equilateral triangle is not a right triangle, and in order to use the Pythagorean theorem, you have to have a right triangle. So I have to give you a 90 degrees somewhere. Well, you got to extend this side. That's terrible. I could do better than that. You got to extend this side so that you add another 30 degrees here. And now this becomes 60 degrees. Now it's equilateral. Yeah, because if this side is 60, then this side, this angle is 60, then this angle is also 60, and this angle down here is also 60. So if this is 8, well then this is 8 as well. And so the total here, I guess I can call this D. Yeah, I'm adding in a vertex. Add another copy. So you're basically reflecting or duplicating. And we're duplicating this thing on the other side. So the total of this side here must be 16. So that's your A. Yeah, remember? A could be any real number. In this case, it's 16. Well, if that side is 16, then this side is also 16. And then this side is also 16. So there is the equilateral triangle. So what am I asking for? What will I be asking for? I will be asking for angle B. Right. I actually won't ask for D. Right. D was just temporary so that I could get the equilateral triangle. I will be asking for angle B. Angle B is 60 degrees. Yeah. If I already gave you one of them was 60, well, then the other one would be 30. All right, because remember, the total here has to be 180. Okay. I will also be asking for AB, the hypotenuse. So AB will be 16. And then the hard one, or the more complicated one, is AC. So I'm going to use the Pythagorean Theorem. Pythagorean Theorem. Now this is tricky because I added in this other triangle here. So when I use the Pythagorean Theorem, I want to ignore the extra piece that I didn't use. I only used that side to figure out that this was 16. Right. Once I'm done with that, I don't need it anymore. So now I've got c squared equals b squared plus a squared. I'm actually going to write it this way. B squared plus a squared equals c squared. Why am I doing it that way? Because I'm trying to find this side here. Yeah. So this is C, this is B. I know I called this A a minute ago. I really should have just called it X. I regret not doing that, but A is actually here. Oh, this is actually B, and this is A. So A is now half of what I was calling A a minute ago because I'm ignoring that side. And I hope I'm not discouraging you from studying trigonometry. I really wanted to end with this type of example. I didn't mean to bite off more than I could chew. So my question is, what is B? Yeah, B is AC. Trying to follow the classical notation there. So B is my unknown. A is 8. C is 16. So 64. I think that's 256. I'm trying not to use a calculator. Subtract 64 from both sides. 256 minus 64 is 192. If b squared is 192, then b is the square root of 192. I should try to simplify if possible. Let's see. I'm going to cheat it out a little bit because we're getting low on time. I know I said not to use your calculator, but how about this? Only use your calculator if it produces whole number values. Don't ever give me decimals. So I'm going to do 192, let's see, divided by 16, 12. I'm trying to simplify the square root of 192. So that is 16 and 12. Double check that. 192 divided by 16 is 12. Yeah. 16 is perfect. So that becomes 4. Now 12, I probably would be okay if you left it, but this is my last example today, so I'm going to go a little further. 12 is actually 4 times 3. Yeah. And 4 is again perfect. So 4 becomes 2. The square root of 4 is 2. 3 is where we have to stop. Yeah. And then 4 times 2 is 8. Square root of 3. And again, I more than likely would accept 192. In fact, I will. But I do want you to know how to simplify. There are some problems that insist that you simplify. So really, this is just a demonstration on simplifying so that you have the experience before this chapter is over. So that's going to be 8 times the square root of 3. That's the trickiest one. That is when you get to the end of 5.8, there's a couple zingers in there, but I intentionally want you to deal with them and to get over it, right? And you'll be fine. You'll be fine. You might actually notice another pattern here. All right. This is a 30, 60, 90 triangle. So again, you could memorize this if you like. This is optional. If you have a 30, 60, 90, it's basically half of an isosceles triangle. Sorry, half of an equilateral triangle. It's not an isosceles, equilateral. All right, so half of an equilateral triangle. There is a very familiar pattern, which in Math 5, trigonometry, this becomes not optional. If the hypotenuse, so there's 30, there's 60, and there's 90. And in my example, I drew it upright. It really doesn't matter which way it's oriented. This is the way I usually have it oriented in the homework. Most of the homework problems are oriented this way, but I was trying to show that relationship, so I intentionally drew it upright. Okay, whatever the hypotenuse is, okay, this is half of that. This side is half of whatever the hypotenuse is. And then this side is the same as that, multiplied by the square root of 3. Okay. There's actually an easier version that I also teach. If you multiply everybody by 2, if you multiply everybody by 2, you get a much larger triangle. Then this is 30. This is still 60. This is still 90. Then this is x. This is 2x. And this is x times the square root of 3. And again, this is not required. This is optional if you like patterns. All right. Some people like the pattern because they can look at the problem and go, oh, if that's 30, that's automatically 60. You don't have to do a whole lot of calculation. If this is 16, the long side, well, then this side must be 8. Right? So there's 2 different ways of thinking about it. You can think of this is x, or this is half x, or you can think of this is x and then this is double x. But either way, the relationship is that the short side is half of the hypotenuse. And then the base side, the second longest side, is the short side, x, multiplied by the square root of 3. Well, again, the lesson is the Pythagorean Theorem. So if you're looking at me right now going, Dr. Jordan, you've gone on too much. It's okay. I did that on purpose. I did that to catch your attention a little bit. If you got the Pythagorean Theorem and you understand the basic nuts and bolts of how that works, then you'll do just fine. All right, you'll be okay. That's the most important thing. I just got a little carried away with the trigonometry and the classical stuff, and I put these in the homework. So how you solve them is entirely up to you. But I finally finished. All right, that's it. We're done with chapter 5. Chapter 6 is the last chapter. I'll post that next week. So we're done for now. So until we see each other again, this is Dr. Jordan. I'll see you on the internet.